morning. In this program, I'm going to take you through organic chemistry. Welcome. The term organic chemistry comes from the word organic, which means any derivative from one's living species, like plants or animals. When you talk about organic compounds, we'll find that organic compounds are hydrocarbons, and hydrocarbons are of varied range. There are hydrocarbons which are exclusively carriers of carbon and hydrogen, and the other hydrocarbons which carry both oxygen, carbon, and hydrogen. Now, in this case, we are saying that an organic compound is a hydrocarbon that forms naturally from dead organic matter. And this may include plants in form of humus and animals in form of fossils. The main components of organic compounds are therefore carbon, hydrogen, and oxygen. If, for example, I combine carbon and hydrogen, I will form CH2, which is the homologous species. This will multiply by addition of hydrogen and will form what is known as methane. Now, methane is an alkane species of organic compounds. In the same step, we may have a reduction of methane into CH3, which forms an alkyl species. And when that happens, it provides room where we could have the CH3 radical combining with an OH molecule, namely oxygen and hydrogen, which forms hydroxyl. And when they combine, they form CH3OH, which is an alkanol. And therefore, we find that all organic compounds are derivatives of the homologous species, represented as CH2. The homologous species may combine with hydrogens exclusively, forming alkanes. It may multiply itself without hydrogens, forming alkenes, and may continue multiplying itself and reducing hydrogens, forming alkynes. The sequence of addition and subtraction of hydrogen molecules may lead to formation of a varied range of organic compounds which exist in different families. In this case, since all organic compounds are derivatives of the homologous species, the different organic families are referred to as the homologous series. Let's take a look at a few of them. So, at this point, we have homologous species, which is the CH2 as described. Now, the homologous series include alkanes, alkenes, alkynes, alkyls, and the rest, as you can see there. Now, I'm going to look at each of them briefly. First, the alkanes. Alkanes are single bond hydrocarbons with the general formula CnH2n plus 2. An example of this is methane, which is CH4. Next, we have alkenes. Alkenes have the formula CnH2n, and the example we have there is ethene, which is C2H4. Now, the third is alkynes with the general formula CnH2n minus 2. So, in this present case, we have an example. Example here will be ethine, which is C2H2. Now, the three principal organic series of alkanes, alkenes, and alkynes represent the fundamental groups from which other derivatives are obtained. However, when you look at alkanes, alkanes are said to be saturated hydrocarbons in the sense that they are composed of single covalent bonds in which each carbon holds a network of 4 single covalent bonds. Number 2, alkenes and alkynes are unsaturated since they carry double bonds and triple bonds respectively, and in this case they have room for addition of other species by the breaking of the double or triple bonds. So when we say that a hydrocarbon is saturated, it simply means it carries a network of single covalent bonds and has no room for addition. When you say they are unsaturated, it means therefore that they carry either double or triple bond and have room for addition. When you go to alkyls, alkyls are radical forms of alkanes, just like methane changing to methyl. So their formula is CnH2n plus 1. If you compare the two, you'll find that the formula of alkyls corresponds to the formula of alkanes with a deficiency of 1 hydrogen. In each of these formulae, N represents the number of carbons, while the number of hydrogens is determined from the value of N, which means if you know the number of carbons in a given species, you can use it to determine the number of hydrogens using the respective formulae. And next we have alkanos, and alkanos have the general formula CnH2n plus 1 joined to OH. In other words, they are derivatives of alkanes and formed from alkyls. So if R is an alkyl, you just add OH and that forms an alkano. The example of this would be methanol, which is CH3OH. Next we have alkanoic acids. Just like the alkanos, alkanoic acids are derivatives of alkyl species, and in this case their formula is CnH2n plus 1 joined to COOH, or in the place of the formula we have R for alkyl joined to COOH. Now COOH is referred to as the carboxylic group. So the carboxylic group is COOH. It is composed of a carbonyl joined to a hydroxide. In this case, when the carbonyl joined to hydroxide, we refer to it as the carboxylic group. Now, when the carboxylic group gets an alkyl, such as methyl, ethyl, propyl, and so on, it becomes a carboxylic acid. The first carboxylic, however, does not carry an alkyl. In its place, it carries hydrogen, and then it is known as methanoic acid, or in common terms as formic acid. Next to the alkanoic acid, we have aldehydes. Aldehydes are derivatives of alkanos, and they are principally primary organic compounds of the formula R, C, double bond O. In this case, the double bond of the carbonyl is formed at the outermost carbon or primary carbon. Aldehyde have similarities with ketones. Now, ketones are secondary hydrocarbons with the formula R, C, the double bond O, and R. In this case, we find that between aldehydes and ketone, the carbonyl molecule creates the distinction. The carbonyl molecule in ketones is a secondary carbon, while the carbonyl molecule in aldehydes is a primary carbon. Beyond this, we have other derivatives of organic acids, namely ethers and esters. So briefly, if you allow me just to describe that, we are going to say that ethers have the general formula R, O, R. For example, methyl oxide or dimethyl oxide. The example here is dimethyl oxide, which is methane joined to oxygen and methane again. So this is dimethyl oxide. Another example that we have is what we are calling the esters. Now, esters have the formula RCOOR. For example, we can have methyl ethanoate. That is methyl ethanoate. Good. So this is the primary representation of the different organic series. Now, beyond this, we can say that organic compounds are either aliphatic, which means single-chained or long-chained, or aromatic, which means cyclic. Let me take a look at that briefly. So the classification of organic compounds are of two main forms. One is aliphatic molecules. These are straight chain hydrocarbons. For example, we may have 1, 2, 3, 4, 5, 6, and joined with hydrogens and a network of what forms hexane. So this is a hexane molecule. It is straight chained, so we say it is in the class of aliphatic molecules. Now, 2, we have the aromatics. The aromatic molecules are cyclic. We may take the same hexane and represent it in a cyclic form where it forms a hexagon, and then the attachments of hydrogen are projected on each terminal. And in this case, this becomes what we are referring to as the aromatic hexane. The distinct difference between aromatic and aliphatic is the number of hydrogens. Because it is cyclic, there is a deficiency of 2 hydrogens. In the name of, when we look at the hexane, we may say it is C5H12. However, when you look at the aromatic hexane, it is C5H10. C6H12, sorry, let me correct that. Hexane is C6, so we have C6H14, while the aromatic is C6H12. The difference is 2 hydrogens. And therefore, in summary, we have said that organic compounds are hydrocarbons in which some carry oxygen and some do not. The main organic families are the alkanes, alkenes, alkynes, alkyls, alkanos, alkanoic acids, aldehydes, ketones. And then we have subsidiaries like ethers and esters. We have said that to represent the chemical formula, we use general formula in which N is the number of carbons. So long as you know the number of carbons, you will be able to determine the number of hydrogens in each organic series. And that serves the purpose of introducing us to organic chemistry. Next, we are going to look at each family independently and describe its physical and chemical characteristics. Welcome.